This is JY, co-founder of Data Mechanics, and I'm going to give you a product tour of our serverless Spark platform. So as you know, Spark is the #1 big data engine out there. It's very popular because it's fast, it's versatile, and it's easy to write Spark applications in one of the high-level API like Python, Scala, SQL, and more. However, the hard part with Spark is typically infrastructure management. There's a lot to set up, it can be slow to use and iterate on, and there's a maintenance aspect. This is the pain point that we set out to solve with our serverless Spark platform. It's fully managed, it's containerized, in fact it's deployed on Kubernetes, it's very fast, very reactive, say goodbye to coffee breaks, and our platform is going to automatically and dynamically optimize all the infrastructure choices and these knobs that Spark exposes to make your applications fast and performant. This was the starter point of our project. We gave a Spark Summit talk last year about how it works, but concretely we're going to be tuning container sizes, disk sizes, instance types, Spark configurations around parallelism, memory management, I/O, and it's going to give you a significant performance and stability boost. Now let's talk about the architecture of the platform. As I said, we are deployed on a Kubernetes cluster inside our customer's cloud account. This is very important for security and data privacy reasons. It means our customer's sensitive data doesn't leave their cloud account. In fact, we could almost cut off this Kubernetes cluster from the internet. We are available on AWS, GCP, and Azure. Now, when it comes to using the platform in practice, you would either connect your notebook, like a Jupyter notebook, or submit applications programmatically using a script or using a scheduler like Airflow. And this would hit our gateway, which is the entry point for launching Spark applications. And then the gateway is going to actually launch the Spark apps, configure them, scale them, and give you access to a monitoring UI. And obviously, the Kubernetes cluster doesn't have a fixed size. Everything is going to be automatically scaling up and down based on the load. All right, let's move to actual demo. So first, I'm going to connect a Jupyter notebook and play with Spark interactively, and then submit some applications programmatically too. So let's run a Jupyter notebook from my laptop. I'm going to run this command, which is going to open up the traditional Jupyter interface on my laptop. But there is this additional parameter, gateway URL, which tells Jupyter not to run the commands locally, but to submit them to the Data Mechanics cluster. So when I run this, the files that I see here are files, local files on my laptop. But when I open up a notebook, automatically it's going to spin up a Spark application on Data Mechanics. So if I log in to our demo cluster, I can see here that there's a notebook app, which is pending, which was started a few seconds ago, and is actually already running, which means I can run my code. So in this notebook, I'm going to install some Python libraries. I'm going to read in some data, which here is hosted on GCS, but this could be any data source supported by Spark. I'm going to run some SQL queries, do some plots. If I go back to our monitoring UI, I can see that it's indeed running, but right now it has 0 CPU cores, which means it can't run any Spark tasks because there is no Spark executor. However, as you can see on the right, dynamic allocation is enabled. So right now, probably Spark is asking for more resource to actually run the application. We can confirm this by looking here at the bottom, and we can see the Spark driver logs, which are being streamed live. And we can see here that we're requesting 1 executor from Kubernetes. And as soon as this executor comes in, we're going to start processing tasks. It looks like actually this is the case. Yeah, in fact, we have 4 CPU cores. At the top right here, we have the bottom that opens up the Spark UI, and this is going to be available obviously for live apps, but also from terminated apps by spinning up a Spark history server. So while the notebook is running, let me now kick off maybe 1 app using the API and 1 app using our Airflow connector. So for the API, I'm going to make a post request on this URL. And one thing I want you to take a look at is that here I can provide a path to a Docker image in my API call to specify the base Docker image that Spark should use. And this is a great way to package your dependencies. So I just click send, and now if I go back and move back to applications, I see my notebook that's running with 4 CPU cores, and this new app, which is right now pending and in fact, again, running. So when the app starts in less than 10 seconds, it's typically because Kubernetes already had some node ready to be running your app. If there is no node with capacity, it typically takes a minute and a half, but it's still pretty fast, to get a node from the cloud provider. Let's now open up Airflow. So Airflow is not something provided by the platform. Typically, our customers either use Airflow or some other kind of scheduler like Amazon Step Function, Google Cloud Composer. But I'm going to show Airflow in this example. We have an Airflow operator, and just like our API, in this case, I haven't supplied a Docker image, so it's just going to use one of our base pre-built Docker images. But I'm going to specify the code it should run on by providing, a path to a certain jar. And I could also obviously specify dependencies this way, and I can obviously also specify any kind of Spark configuration that I want. So let's trigger this. And if I go back to our monitoring UI, we can see that the notebook is still running with 4 CPU cores. We can see that the app that I kicked from the API is now running, and it still needs some CPU cores. So probably here the cluster is spinning up new nodes to actually get CPUs here. One thing that Spark on Kubernetes is really good at is both making sure each application is fully isolated, okay, because each app has its own Spark driver, its own set of Spark executors. You could be using a different Spark version, you could have different Docker image, different dependencies. But at the same time, you really benefit from having a shared infrastructure because because the underlying nodes are shared, and so one app could benefit from capacity that was released from another app, and Kubernetes can reallocate capacities across the cluster really quickly. So you get the benefits of a shared infrastructure while each application is also running in full isolation. We can see that one of the app I kicked earlier has just completed. Right now, it's probably processing some stats, and we're going to see some stats around the CPU that was used, around the total I/O. And as soon as this app completed, the 2 other apps quickly started. So typically, this is an example of this reuse of resources in action. And so here, as I was mentioning, as soon as an application finishes, we compute some statistics like the volume of data was read and written by an app, and so on. Let's look at these statistics now on an app that's been running more regularly. And so here we can track them, kind of day by day. So some of the statistics we compute is the duration of the app, the volume of data that was read and written, the CPU uptime, which is a good indicator of your cloud costs. And so you could be tracking this in this UI, and you could answer a question like, is my ETL app getting more performant, or is it processing more data, or was yesterday run an anomaly and that I should look into? And here you have the history of all your runs, and so you could indeed be looking at a past run and digging through the Spark driver logs, which you can download, or digging through the historical Spark UI, which you can bring back to understand really the performance of your app over time. Okay, that's it for today. As a reminder, we are available on AWS, GCP, and Azure, so feel free to hit us up if you're interested or if you just have feedback. Thanks so much for watching. Bye-bye.